get started. So I have a different arrangement today. Just want to make sure everyone is able to hear me. You guys able to hear me? Okay, sounds good. Great. Any disturbance, any noisy stuff today? Okay, sounds good. Great. All right, so we'll get started. We're going to work on discussion 13. And the way we are going to do this is I'll first give you an overview of why we are doing this ANOVA and why do we why do we have to do this at all. And then we'll walk you through two examples or two questions. And the way these questions are designed is I've designed it so that you go step by step and we reach till the end where we can draw conclusions. But the way this is done is broken down into steps so that you understand at each step what is it that we really are doing. Before we get started, just a couple of announcements. The first announcement is about your graded homeworks and quizzes. So I've graded all of them so far, except the homework that you turned in yesterday. If you have any questions or if you have anything that you think was graded incorrectly, do let me know. My office hours again are the same on Tuesdays between 3 to 5. Happy to take any questions. The second announcement is about the project, which is the first part of which is due tomorrow. And the way what we expect from you in this part is, so I've already put in a template, which you're expected to go through and read in terms of what is it that we really expect. And it's going to be a very simple exercise. What you're essentially going to do is just find out a data set on which you can likely run a ANOVA or a regression analysis and just write about how you found the data set, what kind of columns would be what you would be working with, right? So it's a very simple exercise. I got a question yesterday asking me about the validity of normality. So, I mean, the assumption, do you have to check if the normality assumption is satisfied or not? And it's a great question. The way we thought about part one was you don't have to do the analysis at this stage. So you don't really need to check for normality. You will check for that when you're doing part two. And when you do that, if you go through the questions, you'll notice that there is a question which asks about plotting the residuals. And at that stage is when you will tell whether the normality assumption was satisfied or not. Okay, so don't worry about whether that data is normal or not at this stage. Just make sure you find something which has a discrete, a categorical variable and a continuous variable. Okay, any questions about the project or anything in general? Okay, all right, so we'll get started. And what we are going to do is we're going to work on ANOVA. Okay, I'm going to switch off my video because you'll not be anyway, my face will be on my screen anyway, so it's not going to be useful. Okay, so in ANOVA analysis, what is it that we are interested in? So it's essentially, in some sense, an advanced version of what we have been doing so far. So we have group one, we have group two, but this time, so far, we have been only working with two group data, where there was, let's say, a control and a treatment group. Now, this has been generalized. Okay, so you have more than two groups. And the hypothesis that you're interested in, again, testing is very similar to what we were doing last time. Okay, so you're essentially interested in testing whether the means of these three groups or more groups are same or not. So there could be two strategies of doing this. One strategy would be, so this is your strategy. One pair strategy would be to do pairwise t-tests. And the second strategy would be to do what we call ANOVA. And to be specific, this is one-way ANOVA. Okay. So let's talk about first strategy first. So in terms of first strategy, the assumptions that need to be satisfied are, you're already familiar. So you have assumptions of normality, or let's approximate normality to be specific, and simple. The problem, however, what's the problem is this approach will lead to an inflated type 1 error. Now, what do I mean by that, right? So we have, let's say you have a false positive. So essentially rejecting the null hypothesis when it actually indeed is true. So you would have type 1 error, and this error, the type 1 error, is 3 times approximately. Okay, this is not exactly, but this is essentially type 1 error of each test. Okay, so this strategy is actually leading to a higher false positive, a number of false positives, and hence you'll have like an inflated type 1 error rate. The other problem is obviously this is also computationally challenging. So right now you only have 3 groups, but what if you had like 10 groups? So you'd have to do, let's say, 10 choose 2 tests, which is a lot. Okay, which is a lot. So we want to avoid this. And the other thing, and the way to avoid this is to do ANOVA. Okay, so there's one more advantage of doing ANOVA. So ANOVA is essentially, in some sense, it's doing pairwise t-tests, but it's doing it in a smart way so that it also accounts for the heterogeneity that exists in the data. And what do I mean by that? So it accounts for, it pools the variance between and within groups. Okay, so in some sense, it's accounting for the variance in a much more advanced fashion than what t-test does. Okay, and these are in some sort of, I'm using blanket terms, and I'll clarify each of these blanket terms as I move along. Okay, so the motivation to do ANOVA is we are interested in doing multiple, in testing these hypotheses where there are multiple groups involved. And we can't really do a t-test because the t-test would lead to an inflated type 1 error rate. Okay, that said, there are still assumptions that need to be satisfied, and the assumption among these groups are, first of all, so these are assumptions for ANOVA. The first assumption is approximate normality for each of the individual groups, and the second is they're obviously simple random samples, and the third is you have approximate equal STs or variants within each group. Okay, so these are not very hard assumptions, but these are kind of the required assumptions that we need for doing an ANOVA analysis. Okay, okay, so let's get started with the problem, and I'll explain each of these assumptions as we move along. So the problem here is about this particular college administrator claiming that there is no difference in the GPA between 3 different schools. Okay, so you're given a very small data set, which has just 4 points. And these 4 points are essentially GPAs coming from each school. Okay, so the first question asks us to state the null hypothesis in words and simples. So that's very simple. There is no difference in the GPAs. Okay, and this essentially, if I call this 1, 2, and 3, this essentially is mu1 equal to mu2 equal to mu3. Okay. Next question, what sort of testing would you apply to test the hypothesis? Okay, and this is in some sort rhetorical question given that we're talking about ANOVA, but this would be ANOVA. Okay, and why is it ANOVA? So one clear check here is there is one categorical variable, which is the school, and there is one continuous variable, which is your GPA. Okay. And these sort of settings where you have these categorical and continuous variable, and you're interested in testing the difference between the means or equality of the means, is your choice would be ANOVA. Okay. And in this case, to be specific, this is one-way ANOVA because we have just one categorical variable. Okay, which is, sorry, this is school. All right. And let me be specific, this is one way. All right. What would be a potential problem employing a pairwise t-test for the three groups to prove or disprove the claim of the administrator? And we have already seen this. First is you have inflated or increased or higher type 1 error. And the second is, in some sense, more of an advantage of doing ANOVA, which I already kind of briefly talked about, is that ANOVA will combine the variability information. Okay, and this in some sense leads to a higher precision. Excuse me. Okay, so in some sense, ANOVA is taking care of all the variants that exist in the data in a much more smarter way than what t-test is doing. And you can imagine why is that happening, because the t-test will look at only two groups at once. Okay, but the ANOVA is looking at all the data points all across all the groups at once, and hence it's combining this information of the variants that exist in the data in a much more, uh, let's call it advanced, in double quotes, fashion. Okay. All right. So how many degrees of freedom are there in ANOVA? Okay. So this is kind of a very big jump from previous question. We directly are talking about degrees of freedom. So given there are multiple groups, you can imagine what the data really looks like. So you can imagine that these four data points will lead to something called the within variance, right? So not every data point which is in the same group is exactly same. There is some variability going within the same group as well. Okay. Secondly, there is also variability between the groups. Okay, oh, type 1 error. Okay, so there's a question about what type 1 error is. Okay, so let me give you a quick overview of what I mean by type 1 error. Okay, so I mentioned here that you have type 1 error. What does type 1 error mean? So remember, recall when we talked about t-test, we gave it certain alpha, right? We gave it certain level of, so alpha is your threshold of significance. Okay. And what does alpha actually equal to? So alpha is essentially the probability that so this is your t statistic. So I'll call it t. Let me call this entire thing t. Okay. And let me call this particular point as t alpha. Then this is what your type 1 error rate is. Now, this is essentially equal to your type 1 error rate. Now, what does that really mean? Okay, so imagine you had a data point coming from uh, this particular spectrum of the distribution. Okay, in that case, your p-value that you would calculate. So let's say your test statistic is, let me use a different color. I can move my screen. Okay, yeah. So imagine you had certain point which was falling here. Okay, so this is your TS. This is your test statistic. Now, the p-value associated with this p-value is definitely going to be less than alpha. Okay, why? Because the probability that it exists here or in the extreme, again, I'm talking about one-sided test, but everything applies in double-sided test as well. So this is the p-value, right? So this is your p-value. Okay, and the alpha, this is your alpha. So this implies that, let me use a different color. So this implies that your p-value is less than alpha, but this is leading to a false positive because you know that this data point actually exists here, but you're still going to reject the null hypothesis. Okay, and hence this is equal to your type 1 error rate. Okay, does that make sense? Okay, okay, where was the actual point? Okay, so the actual point, the statistic that you're testing is, so this is your T statistic. Okay, now if it falls anywhere in this regime, okay, what is this regime? This regime is a point which is some T alpha. I don't know what that T alpha is, and I don't really care about it. All I care about is I first calculate the p value associated with this t statistic. Okay, so these two conform to each other. Let me use the same color. Okay. So these two are analogous. The moment you get this t statistic here, which is lying here, you can calculate the p value associated with it. And once you calculate this p value, notice that your alpha, which is the entire probability of this shaded region, which is blue, which also actually happens to include the red stuff, then p-value is this small area, which is going to be less than alpha. Okay. And hence you're going to reject it. And why is it false? Because you know that this point actually belongs to the null hypothesis. It actually belongs here. Okay. What would be the other scenario, right? So the other scenario would be if it actually did not belong to this, then on the same axis, it would have light somewhere here. Okay, now this is H1, this is H0. Okay, does that make sense? So TS actually belongs to your null, and that's why. Okay, all right. So that was a digression. We'll move on to, okay, any other questions about this? Any type 1 error rate? Okay, so then I'll proceed. And I was talking about variability. So there is two sources of variability. These two sources of variability are within and between. Okay. And this within comes because there is variability within the groups. That is, if you pick up one group, the data points are not exactly same. There is variability. And there is also variability between the groups because uh, not all the readings in each of these groups are equal among all the groups. Okay. So we have 2 degrees of freedom. The first one is called between, and that's the simplest to calculate. So you have, how many groups do we have? We have 3 groups, right? So each point in calculating the between degrees of freedom acts as, each group acts as one data point. Okay. And this is equal to 3 minus 1, which is 2. Okay. Let's see what will happen in the within case. Now in within case, what we essentially say is let's treat all the data points to be the same. So you forget about that there is actually a difference coming because of the groups. I mean, you forget that there are groups information. So the total number of points that you have. So this is, let me write this as n dot minus I. Okay, and I'll justify why it is like this. So n dot is where n dot is equal to 4 plus 4 plus 4. Okay, these are the total number of data points you have. And then from these, you're subtracting the number of groups because these points in some sense are constrained by the group that they come from, right? So if you know the group of the mean, if you know the mean of each of these groups, there are 3 means that are known to you. And in some hand wavy fashion, that's the kind of information that you're going to subtract from this to get the within degrees of freedom. Okay, so that's 9. So we have 2 degrees of freedom between and within, and we are going to use this in the next part of the question. So the next question asks us, calculate the pool standard deviation. And that's again a simple number to calculate. So this pooled standard deviation is given by a kind of a big formula, but we'll see how we come at that particular formula. So imagine the standard deviation of group 1 is S1, of group 2 is S2, and of group 3 is S3. Okay, so you're given the standard deviation of these groups. So how do we calculate the pooled version? So we have already seen this when we were doing the t-test. The way we do this is You multiply ni minus 1. Ni is the number of points in each group minus 1 times the SI square. So if you know the formula of SI square, you know that this particular term happens to be in the denominator. So you're essentially multiplying it by by its denominator. And then finally, you're summing it up. You're summing these values up across all the groups. So we have 3 groups. Okay. So essentially what you're doing is you're pooling all the deviation across all the 3 groups. Okay. And there's one more way to write this. This is also equal to, the numerator remains the same, but this quantity in the denominator, if you sum up all the values, you'll notice that you will get at this particular number, right? So n dot minus I, where n dot is the total number of data points you have in your data. And I'm going to give you the values for all of them. So S1 is 0.016, S2 is 0.083, and S3 is 0.029. Okay, so notice that this information was actually not provided to you. So you need to calculate these values. And how do we calculate this? So if I have to calculate S1, it's very simple. You already know this. So this is all the 4 data points. You just have to calculate the standard deviation of these 4 data points. Okay, that's how you get your S1. It might not be given to you every time. In this problem, it's not given, so you need to calculate it. So these are your final values, but this is how you would get it. So Y1 is the represents all the points coming from group 1, and J represents which data point that I'm looking at. So J goes from 1 to 4 because there are 4 data points. And then I'm looking at Y1 bar, which is the mean of the values in the first group, divided by, Ni, which is N1 in this case, N1 minus 1. Okay, this is square. You can take the square root to get S1. Okay, and if you just plug in all the values here, you'll get the pooled value as 0.206. Okay, we'll move ahead. Problem 4, F. You have to calculate SS between and SS within. What is SS between? So SS between is the sum of the squares between the groups. And this, in a sense, essentially, you will have access to the cheat sheet or to the formula sheet. Let me first write it down and I'll explain how we reach there. Okay. So the first term is between the groups. So you are looking at, in this sense, you're essentially collapsing all the information within the group to its mean value. And then you're then calculating how different is it from the entire group mean. Okay. So what is YY bar here is essentially summation over I equal to 1 to 3, summation of J equal to 1 to 4, Yij upon N. Okay. And this formula looks very big, but it's nothing actually. You're just summing up all the, okay, I can't. You're essentially summing up all the values that you have in the data, all the data points that you have divided by the total number of data points that you have, right? Which happens to be 12 in this case. Similarly, SS within, this is essentially nothing but what we already saw in some sense, the pooled variation. So this is given by Ni minus 1 times Si squared. Okay, so you're looking at the standard deviation squared of each group. You're multiplying it by the number of readings, and then you're just summing it up across the 3 groups. Okay, so if you calculate these values, this value will be 0.384. Sorry, this is 0.8817, and this is 0.384. Okay. Next, we are asked, how do you calculate the total, and can you verify the relationship between within, and total? So this, I'm going to cheat a bit, and so SS total is, the formula is this. Again, it's a very simple formula to understand. So this is the total variation in terms of sum of squares. So you're looking now at individually each of these data points. You're looking at how different are these data points individually from the group, the grand group mean that you have. Okay. So in some sense, you're calculating the standard error or the standard deviation using the grand group mean as your mean, and rest of the readings just follow. Okay, so I equal to 1 to 3, there are 3 groups. J equal to 1 to 4, there are 4 observations within each group, and you're dividing by the total number of readings that sorry, there's no division here because it's the summation of all the values. Okay, so you'll have access to these formulas, but you need to be able to understand that these are essentially the summation of uh, these are essentially in some sense um, how do you actually get at this formula. Okay, all right, so I said I'm going to cheat a bit, and that cheating involves using the known relation. So this is essentially equal to within plus between. Okay, the reason I'm cheating is because I don't really want to carry out this long calculation, because there are 12, if you notice, there are 12 terms to be added and subtracted. So I've already calculated the within and the between values, so I just sum these, and that will give me the total variation. Okay, and the final value is 1.0888. Okay, everything clear so far? Any questions? Okay, move on to H. Now we are looking at it's asking us to calculate FS statistic. Okay, so FS statistic is essentially given by this calculation. Okay, what does it really mean? So again, why are we really calculating this? Why do we care about F statistic? And the reason for that is, like, we were interested in identifying if there is difference in the group means of these 3 groups. In order to calculate that, we have to basically account for the variation that exists between the groups. Okay, so you're looking at mean. This is MS, which is mean sum of squares between the groups, and this is divided by within variation, right? So this is within and this is between. Now, why are we doing this, right? Why do we care about this at all? So one naive way to look at these differences would be to just look at the between variation, right? But the problem with just looking at the between variation is, if there is a lot of within variability. Now, what is this within variability? If there is a lot of variation within each group itself, then you'd obviously expect some difference between the groups to be arising just from that fact. Okay, so this statistic that we are calculating, in a sense, the denominator is taking care of the fact. Sorry, I'm having scroll issues again. Okay, yeah. So the in essence, the statistic captures that how much amount of between variation do I see, having adjusted for the variation that exists within the groups. Okay, so you can intuitively think about that. If this statistic is high, that means there is a lot of variation between the groups, which is not really being explained, or which is not being explained by the within variation. Okay, so if this statistic is high, that means the the between variation that you're seeing is also high, and that means that the probability that this is going to hold will go towards 0. Okay, okay, all right. So we need to calculate these two quantities. So we have all the ingredients that we need for that, and this is SS between by DF between. Okay, and if we calculate this value, this comes around to 0.44, and the MS within correspondingly is given by 0.042. Okay, so what really is happening, right? So this within value is very small, whereas this between is slightly larger. Now you can imagine, if I divide these two values, it's going to be a large number. And you can see why that matters. The within variation is small. That means if you look at each individual group, there is not much variance going around there, but there is a lot of variation between these three groups. Okay, and that's why your statistic is high, and hence it's quite likely that you're going to reject the null. Okay, so your F statistic, if you calculate, I think comes around to be this value, 10.49. So we need 2 degrees of freedom to quantify this. So F statistic in some sense is M by N. Okay, these are degrees of freedom of between, and these are degrees of freedom within. Okay, this is not Fs equal to, but Fs involves these many degrees of freedom. So you go to table, your chi-square table, and you're looking for degrees of freedom between, which is, so I've already circled it, but you will look for degrees of freedom equal to 2 with a denominator degrees of freedom equal to 9. And this value of 10 lies somewhere between these two values. Okay, so your p-value is, so in all these cases of where you're using the ANOVA tables, it's all of them are going to be uh, non-directional. Okay, so you don't have to worry about any adjustments, luckily, in this case. So this is going to be your bracket for p-value at alpha equal to 0.05. You're going to reject. Okay, and that also answers your final problem, which is I. Okay, any questions so far? I went pretty slowly, but if there are any questions, happy to take them. Okay, now I'm going to, sorry about that noise. There's a construction going on next to my house. Okay, are you guys still able to hear me? Just give me a second. Sorry. Excuse me. I'm in a meeting. Can you stop? I'm in a meeting. I'm in a meeting. Can you stop for around half an hour? Sorry. Okay. All right. So we move ahead to talking about um, a two-way ANOVA from one-way ANOVA, and the way we do that is why we care about it, right? So in our first problem, we only had one categorical variable, which was a school. In this case, we have two categorical variables, right? And this categorical variables are given by two sources of variation. The first one is your editorial, and the second one is your political party. Okay, so in terms of your problem, you're essentially looking at some numerical quantity. This numerical quantity is given by some measure of attitude that you have, right? So this is a referendum, and this referendum is being collected from three political parties: Republicans, Democrats, and Independents, and they are being collected across different editorials. Okay, so this is both of these are categorical, and there is one numerical value associated with it, which is your referendum. So we are interested in finding if any of these editorial or the political party and their interaction. Okay, so what do you mean by interaction? So let me first explain what is it that we're really interested in. So we have four editorials, 1, 2, 3, and 4. We are looking at some sort of a numerical measure, which is given by, we are looking at some referendum, which is given by some numerical quantity. Okay, so there's one theoretical scenario that if you were, let's say, use a different color. So let's say you were a Democrat. So if this is Democrat, okay, so you're seeing some sort of pattern coming because you're coming from this Democrat, right? Let's say what would we see if we were, on the other hand, let's say if I were a Republican. Okay, so there are scenarios where you're a Republican. So this is scenario number one. Okay. Now, what does it really mean to? Sorry, I'm going to use consistent colors. So, what does it mean to have this scenario? Okay. That means it doesn't matter whether you're Republican or Democrat. You're essentially going to see a similar level of differences between the editorial that you have in terms of your referendum, depending on which editorial you're coming from. There is a second scenario, and this second scenario is kind of interesting. Is It's given by this particular pattern. So let me first draw the pattern. So your pattern for Democratic remains the same. But now, since you're coming from a different political party, it seems to have a different effect. Okay, and this is still your R. So this essentially means there is an interaction. And this means there is no interaction. Okay, so what does it mean to have an interaction? That means that depending on one level of the categorical variable, the response that you see in the other categorical variable in terms of the numerical value that you're calculating is different. Okay, and that's essentially the third term that you're seeing in this particular table here, which is the interaction term. Okay. All right, so we are asked to first thing that we asked is we want to be able to calculate to complete this table. So we'll go in step by step. Let's look at the first editorial. So editorial degrees of freedom are very easy to calculate. That's 4 minus 1. You have 4 editorials. This is 3. You're looking at political party. So we have 3 political parties. So this is 3 minus 1, which is 2. Now, how many degrees of freedom do we have for interaction? That's again essentially a multiplication of these 2 degrees of freedom. That's equal to 6. Okay. The fourth one, which is within, is now very simple to calculate. That will be 179 minus 3 minus 2 minus 6. Okay, and that's going to be 168. Okay. Next, we complete the mean square table, and that's essentially SS divided by DF. So this is going to be 1200, 3600 by 3, 4000 by 2 is 2000, 7200 by 6 is 1200, and next we calculate the FS statistic. So now there are 2 values of FS. Sorry, I need to complete this one as well. This is going to be, okay, so this value here is 23,200, which is the total summation, minus 3,600, minus 4,000, minus 7,200. Okay, and this value, if you calculate, will be 8,400. Okay, so the MS here will be 8,400 by this value here is 8,400 divided by 168. That's equal to 50. Now we are asked the next question, which is part B, is to ask us test whether the editorials affect the referendum, right? Now, what does this mean? So you're essentially saying that editorial 1, editorial 2, editorial 3, and editorial 4 mean effects are same. This is your null. This is what you have to test. Okay, so how do we test this? So it's again going to be our two-way ANOVA. So we are again going to have to work with FS statistic. And the FS statistic in this case would be essentially given by 1200, which is a summation of squares that you see, the mean square of that you see for the editorials, divided by within. Okay, so it's always between divided by within. This is 50, and this you get as 24. The degrees of freedom, so you already know the degrees of freedom, so I'll write this down. Degrees of freedom in the numerator is going to be 3. Degrees of freedom in the denominator is, so I'll call it N and T. Okay, I'll not move to the table to calculate this. And you can trust me on this, that if you have so many degrees of freedom in your denominator and the FS statistic is greater than 1, then your p-value is significant. Okay, so your p is less than 0.001. And hence you reject H naught. Okay, and as a sense, it seems like the referendum has the editorial seems to have an effect on referendum. That means there is a mean difference arising in the group means of the 4 editorials. Okay, let's look at problem C. Problem C is asking the same question, but in the light of the political party. So we have H naught equal to Democrats, Republicans, and independents are equal or not. Okay, so do you see the power of two-way ANOVA? The two-way ANOVA is essentially allowing us to investigate much more fine-grained problems. Because we have two categorical variables, we can test if the numerical quantity that you're measuring is being affected based on different categories or not. Or in the third case that we're going to now work with is the whether the interaction as well. Okay. So the F statistic again is given by this value here, which is 2000. And again, this is between, this is within. Okay, between is coming, this between is coming from the groups corresponding to that particular, right, the political party. Okay, and this is 40. Again, this is P. You'll need to reject H naught. Okay, final part, interaction. Okay, so what is it that we are testing in interaction? And that's a mixed value, right? So I'm going to write this as political party cross Democrats. So it's testing essentially a lot of things. It's testing if the Democrat and so Democrat and editorial 1 is equal to Democrat and editorial 2 and so on is equal to Republican and 1 equal to Republican. So when I write, sorry, let me be consistent. This is and, this is and this is and. Okay, so it's essentially testing the equality of all these groups. Okay, and your FS again is given by 1200 divided by 50, which is again 24. The degrees of freedom in this case are 6, and 168. Again, going to be significant. Okay, so P is, and this is you again reject H naught. Okay, is that clear? Right, so it seems like there is an interaction effect as well. So depending on which political party you're coming from, whether you are a Republican or a Democrat. So let's take a quick example what that means. So what this means is mu D and 1 is going to be different from mu R and 1. Okay, and it's further different between the independents as well. So this this is mu R and 1 is rejected. Okay, and so on. And the quick way to see this is through what I drew here. So this is the kind of case. The second case is the one which is kind of holding in our case. Okay. Okay. Any questions about any of the thing that I talked about? Okay. Let me switch on my video. Okay. Yeah. Any questions? Sorry for the interruption. There was some construction going on.
Hey, Socket.
Yeah.
So you said the interaction for this one was significant, right?
Right.
So doesn't that mean we can't reject the null then? Like, since it's part of the null, like that there's interaction.
So the null in this case was that there is no interaction. So we reject that null. Okay. So that means that there is evidence for the interaction term to exist.
like, don't we usually like stop our analysis if we find that there is interaction? Because like it affects the other variables.
Sorry, can you repeat that again?
Like, I don't know, I was reading online that if there is interaction, that like we can't do any more analysis after that. Like you can't like tackle any other part of the hypothesis, the null.
So the way this is handled is, so you check for whether interaction terms are explaining a lot of variance or not, right? So what did we see? So it's, you can think of interaction essentially as another term being added to your design. And this is essentially a cross version of your two categories. So I mean, I don't know what you mean by stop the analysis. It's essentially we're testing whether you can explain more amount of variance after accounting for the interaction effect or not. Okay, so if there was no interaction, then you would find this particular term to be non-significant. That means
Uh,
you'll not find evidence that the interaction term exists.
Okay.
Okay. Oh, I think okay, I see what you're saying now. Okay, so okay, let me make that clear. So I rejected H naught, right? So when I rejected H naught, essentially that I'm meaning that there seems to be an effect. There seems to be an interaction effect. Between the political party and the editorial. Okay. And if you're doing the same analysis in R, so if you're doing this in R, the way you will specify this is you'll say that my variable referendum is political party and star. Okay, so the star essentially means that it's, let me make that star a bit more distinct. So the star is political party plus editorial. So plus means your normal two categories plus political party colon editorial. Okay, that means that this essentially is accounting for, this is the syntax in R. You might need it if you're doing a two-way analysis, two-way ANOVA, especially from the homework point of view. In the project, we only expect you to do one-way ANOVA. Okay, so this term essentially tells you that if you do this in R, that you are accounting for the interaction effect as well. Okay.
Okay.
Yeah. Any questions? And so if you notice the table, then if this term's corresponding p-value is not significant, that means that in principle there's no interaction term. Essentially, that's how you interpret it. Right. So in the sense, you're saying that if there is no significance attached to this particular term, then I might not have as well taken that into account. So I don't need that term. There's no interaction, essentially.
Yeah. Like when I was looking online at examples of two-way, like they would look for interaction first, and if they found that that was significant,
Mm-hmm.
they would just stop right there. Like they wouldn't even like calculate p-values for anything else because like due to the interaction effect, it skews the results, so they just stop the analysis. That's what I meant by that.
Oh, I see. I see. Sure. So I think, okay, so stopping the analysis is like a very strong term. What you can actually claim is that there is an interaction term, and hence you would have to account for it either way, right? So the interaction can only arise if there is individual effect coming from both these categories, right? And I think that's what probably stopping the analysis means. If you're investigating that the referendum is changing either because of the political party or the
Yeah.
editorial, in this case, if you really find evidence for interaction, then obviously it's holding individually for both of them.
Okay. Thank
Okay.
you.
Yeah. Any other questions? Okay, there's somebody on chat. Okay, so the format of the table. Uh, oh, okay. So what does the? Okay, so we're out of time. If you want to stick around, you're welcome to. I'm going to explain how we reached at this table. So if you want to, I know you might have another class. So if you want to leave, that's fine. I'm just going to talk about what is this table. Okay. So this table essentially is giving you sources of variation on the first column. The second one is the degrees of freedom. The third one is summation of the squares. The fourth one is your mean square. The fifth one is your F statistic. So let's take a quick rundown of what this table is representing, right? So let me see if I have space. So we have Republicans, we have Democrats, we have independents. Okay, this is your column header. Inside each of these categories, we have 1, 2, 3, and 4. This represents your editorial. Okay, now you have data coming from, so this is your header of the table. Then you have 1, 2, 3, 4 again here, 1, 2, 3, 4 again here. So you have certain values coming from each of this. Okay, let's say 0, 1, whatever, something, 2, 3, 4, whatever. Now I'm interested in identifying whether there is a difference in the values of the referendum depending on which group that I'm coming from. So the first level of analysis is at this level, is at the level of the categories coming from the political party. The second question that I asked, so on the first row here, that's the source of variation. Okay, so this source is telling me, so this one, let me follow a color scheme. So this is red, this is green. Okay, so you had this entire table. The first question that you're asking, is there a difference in the referendum values? Is there a mean difference between is there a difference between the mean of these three groups, the Republicans, the Democrats, and the independents? Okay, so is the first row clear? Okay, next, you are also given this information. So there's another level of categories within this category, and this is the editorial level. So we are asking, is the difference that you're seeing in the referendum, is it because of the difference in the editorials that these values are coming from? Okay, and this is your second column. So the degrees of freedom between these two are different. Okay, why is it different? Because in the first case, we only had three groups. So the degrees of freedom are 3 minus 1. In the second, there are four groups. So these four groups, these are the four groups. Hence, you have 4 minus 1. This is 3 minus 1. That's the degrees of freedom column. SS is summation of squares. So summation of squares is essentially measuring how much amount of variation can you expect. So SS. So what is the general formula of SS, right? So SS general formula is very simple. You're measuring the deviance from your sum mean. Okay. This is essentially times ni minus 1. Okay. Let me make that clear more. Whatever number of groups you have. Okay, so this could be infinity. So if you, depending on how many different number of groups you have, SS is measuring how much amount of deviation do we see from the mean value. Okay, now this SS is different for the red versus the green. Okay, the formula analogously is the same, but what's different is when I'm doing the SS for this, then this value, okay, the mean value that you're going to get, that is going to be different from, so if this is SS, all of this is between, this is also between. So the Y bar that I use here will come from editorial 1, okay, or editorial 2, and so on. Okay, so so you'll do it individually within each editorial. So you'll forget about the the first category, the red one. You'll completely forget it. You'll notice, or you'll only focus on the editorials which are marked as 1. You calculate how much amount of summation of squares is being explained by this difference coming from the editorial category. Okay, that's your SS. And your MS is essentially, you divide this SS value by the degrees of freedom. Okay, so why are we again doing this? Because we want to see which of these two groups help us explain the differences that we are seeing. So is there really a difference in the referendum values depending on which column, which category I'm coming from? So is the first question, is there a difference between the referendum values because of the fact that they're coming from Republican, Democrat, or Independent Party? Second question, is there a difference that's coming because of the fact that we have different editorials? And the third question is looking at this in a combined sense. So I'm going to circle that. So it's looking at, it's asking if I'm a Republican and I'm an editorial one, is it different from being a Democrat and an editorial one? Okay, because that could happen, right? So you could have the thing that's common between these two is that the editorials are the same, but whether you're a Republican or Democrat can have a different impact, and that's what is being investigated by the third term, which is the interaction term. Does that clarify things a bit? Okay, let me chat this here. Okay, any other questions? Okay, any other questions? Okay, cool. All right, so if there are no questions, I'll let you go, and thank you. I'll upload these slides and the video lecture, obviously. Okay, if there are any questions, feel free to email me. We can set up if you cannot come into my office hours, I can set up a one-to-one meeting on Zoom, depending on whenever you want. Okay, I'm mostly free all the time. So, okay, all right. Enjoy the rest of your week. Okay, I'll quit.